programming and bug fixing. Let's talk about the two main things done by the programmer. 1. Programming. 2. Bug fixing. Here is a simplified version. 1. Programming. A developer writes. 2. Bug fixing. According to the spec, the child_value must be equal to the parent_value minus 3. So a tester files a bug about plus instead of minus, and the programmer does the bug fixing. Most of the programming takes place during the coding stage, but programming can also take place anytime when there is a need to write, modify, or delete code. Most of the bug fixing takes place during the coding stage, developer finds his bugs, and the testing and bug fixes stage, bugs are found by a tester. But bug fixing can also take place anytime a new bug is found and deemed to be worth fixing. By the way, question: what does a developer do when the programming for the coming release, for example 1.0, is finished? Answer: he writes the code for the next release, 2.0. So, when testers find bugs during the testing and bug fixes stage, developers have to interrupt their work on release 2.0 and fix bugs for release 1.0. The important thing to understand here is that after the developer has done his work for the current cycle, he moves to the coding stage of the next cycle. 3 main types of software bugs. Now, let's learn about the 3 main types of software bugs: syntax bugs, user interface or UI bugs, logical bugs. Syntax bugs. The beauty of syntax bugs is that they are detected and even sort of explained by a compiler if the programming language is C++, or an interpreter if the programming language is Python, once you try to compile or execute the program. By the way, compilers and interpreters are special programs that translate code typed by humans into the language understood by computers. The difference between a compiler and an interpreter is that a compiler produces an executable file but doesn't execute our code. Thus, text files written in C++ must be compiled to become executable or launchable programs. An interpreter doesn't produce an executable file, but immediately executes our code. Thus, text files written in Python are already executable. Example. Let's look at the example of a syntax bug in C++ program. C++ uses compiler. Here is the first program of any student learning C++. Line numbers are not part of software code. This code is saved in the file hello_world.cpp. Let's try to compile this program. As you can see, the C++ compiler refused to compile the program and generated an error message. The bug happened because we didn't close the double quotes after world. How would we describe the bug in one sentence? If we fix the problem, our hello_world.cpp will compile just fine, and we will get an executable file hello_world that prints hello world when we launch it. Example. Let's look at the example of a syntax bug in Python program. Python uses interpreter. Go to test portal, more stuff, Python errors, register with error.py. As you can see, there is a syntax error in line 414 of code. The programmer made a mistake by giving the wrong name of a function. Expected, actual. Here is a bug summary. If we look at line 414 of file register.py, we will see that the function is called correctly, and thus no error is generated by the interpreter. Brain positioning. The only difference between a perfectly working file register.py, test portal, application, source code, register.py, and not working at all file register with error.py, test portal, application, source, code, register with error.py, is a single underscore character. so even the smallest modification to the existing code can break the whole system. That's why regression testing has immense importance. Number 2. User interface or UI bugs. A UI bug is a bug in how the software presents the information. UI bugs range from visual problems like a link on the web page has a wrong color, to interactive problems like it's hard for a user to figure out how to use certain functions. So remember that UI bugs cause presentation problems. 3. Logical bugs. A logical bug is a bug in how the software processes information. Logical bugs are the primary focus of the software testers because, as a rule, it's much harder to find logical bugs than UI bugs, and as a rule, the consequences of releasing logical bugs are much more severe than the consequences of releasing UI bugs. But keep in mind that even UI bugs can be really nasty. If users cannot figure out how to put a book into the shopping cart, then the perfectly working code of the application core doesn't really matter. Here is a stage-by-stage illustration of a logical bug. Example, product design, spec number 98777.2. User must enter 2 integers from 1 to 12 and press enter. Program must print on the screen the arithmetical mean between the entered values. Coding. Here is the code written in Python. That code, also called a source code, is in text file get_average.py. Programmer was supposed to test it, but he didn't. Testing and bug fixes. Let's test it now. According to the spec, our expected result is 5.5 if we use 9 and 2 as inputs, but our actual result is 10, so we have a logical bug. What will you do now? 1. You will file a bug against the responsible programmer. Bug summary, spec 9877 get_average.py, wrong calculation of arithmetical mean. 2. Then the programmer should look into the problem, fix it, and reassign the bug to you. Soon, we'll cover all the technicalities related to bug tracking. 3. Then you must retest the code, and if the bug is fixed, you close it. If the bug is not fixed, you reassign it back to the developer. Let's retest the code now. By the way, we should file another bug against the PM who didn't specify the precise range of inputs. If the max valid input is 12, then the first sentence of item 7.2 must have this wording. User must enter 2 integers from 1 to 12 inclusively and press enter. Why do we need inclusively? Because without it, some folks will feel confident that integers 1 to 12 means that the max value is 12. Some folks will be confident that integers 1 to 12 mean that the max value is 11. Some folks will be plainly confused. So while writing specs, the PM must make sure that everyone in the spec audience will understand the spec the same way. By the way, the spec has another problem. It's not specified how the program should react to invalid input. For example, 0, 13, A, pound, or null input. It's when the user simply presses enter without any data typed. UI or logical bug? Simple question or not? One of the students of a course once asked if an HTML link leads to the wrong page, is it a UI or a logical bug? Interesting question. On the one hand, it's about presentation. On the other hand, sometimes links are dynamically generated by our code. For example, the link logout is generated only if a user is logged in. So our response was, if the misleading link is hard-coded into the HTML code of the web page, then it's a UI bug because there is no problem with processing here, and the presentation is wrong. By the way, hard-coded means that data is static and hence not generated dynamically. Programmer just typed URL when writing his code. If the misleading link is dynamically generated by our code, then it's both a logical and a UI bug because there is a definite issue with processing and there is a definite issue with presentation. Does this make sense? What do you think? I want to mention 2 more things about the coding stage. Version control for test cases. During the coding stage, programmers write code for the coming release and testers write test cases to test that code. We recommended that files with test suites, just like files with specs, should be stored in CVS or other version-controlled system, available to anyone inside the company. The main advantage of storing files with test suites in CVS or other version control system are: it eliminates the risk of an accidental deletion of a file, it allows access to old editions of the file and its history, the file is stored on the shared server, and everyone who needs to, and who has a right to do so, can take that file to execute, modify, or delete existing test cases, append new test cases. You can also use test case management systems for all mentioned tasks. Test case review meetings. It's a good idea to have rules about test case review meetings. Test case review meetings take place before the testing and bug fixes stage and right after the tester has finished writing test cases. What happens is that the following people, the PM who wrote the spec, the programmer who is responsible for coding that spec, and the tester who has finished test cases to test that code, get together and the tester makes a mini presentation about the way he is going to do testing. The tester goes from one test case to another and elaborates about test case idea, expected results, and other relevant things. The great value of this kind of meeting is that in many cases, PMs and programmers give testers new ideas for testing, find omissions and/or errors in test cases. By the way, right after the test case review meeting, send out an email to every participant and to those who are invited but couldn't come to the meeting. In this email, list all the improvements that you've talked about during the meeting. This email is very useful because you'll refresh the suggested ideas in your brain. You'll show others that you understood them correctly. Lesson recap. 1. 2 main activities done by the programmer are programming and bug fixing. 2. When programmer is done with coding for release 1.0, he starts coding for release 2.0. 3. 3 main types of bugs are syntax bugs, UI bugs, and logical bugs. 4. Syntax bugs are caught by the compiler or interpreter. 5. The compiler creates executable file. 6. The interpreter executes the program right away. 7. UI bugs are about presentation. We usually see them in a form of visual problems. For example, wrong font color or interactive problems like confusing layout that makes customers wonder how to use our application. 8. Logical bugs are bugs in logical processing. 9. Logical bugs represent the main focus of software testers. 10. Even one character added or removed can break a working software system of any size. 11. Test cases should be either stored in CVS or inside a test case management system. 12. During the coding stage, testers write test cases. Once test cases are written, test case review meetings should be called, and the PM and developer should review all test cases and provide their feedback.